Okay, moving on to 4.2, we're supposed to start getting into the trig ratios. Well, you guys have probably seen these before, or at least heard of some of them. But if not, that's okay. We're gonna start from the beginning, as if you've never heard of them, and we're gonna be approaching these from a couple of different angles. Uh, the the trig ratios are the sine, cosine, tangent. You got your secant and your cosecant. And you've also got your cotangent. Okay, but let's talk a little bit about the history. And then we will actually get into computing these. So let's talk a little bit about the history. Trigonometry literally comes from the Greek words. Now, I'm probably not pronouncing these entirely correct, but trigonon for triangle, and metron for measure. So literally, trigonometry means triangle measure. And that's what even people way back in ancient times were trying to do, is work with triangles. So they didn't call it trigonometry back then, but they were trying to work with triangles. So all these trig ratios came about in their work, and they didn't all come about all at once. Ancient Egyptians actually used triangles quite a bit. Egyptians used them. They used a very primitive trig in the 2nd millennium BC. So way back when. So this is old. This is old stuff. And they to help them with their pyramids, building their pyramids. And if you look at the pyramids, there's triangles there. You can kind of see they had to know a little bit about them. Mesopotamia, ancient Babylonians, excuse me, they were good astronomers. They were Mesopotamian astronomers. So they had to know a little bit about trigonometry. They were very good at looking at stars, motions of planets, eclipses, etc. So they had to do some work. They looked at the celestial sphere, but in order to work on angles and things, they ended up using triangles and working with triangles. Early Greeks, they used they used something called a gnomon. It helped them to figure out what hour it was from shadows being cast by a rod. Kind of, hold up a rod and see what the shadows are, and then they could tell what time it was. So that was, old early Greeks that had gotten it from the Babylonians. And looking at those shadows, doing the shadow reckoning, they ended up using trigonometry. Okay, so they were doing their shadow reckoning. So there's a lot of ancient people who were interested in angles and triangles, for that matter. And then as they went on, they were using trig to help them measure dimensions of the Earth, distance to stars, and so forth. Okay, but in the modern sense, when you think about trig in the modern sense, let's start with a guy named Hipparchus. from Nicaea 190 to 120 BC. So we're still talking about a long time ago. He was like the most famous astronomer from back then, the greatest astronomer of that time period, that antiquity. But he would be looking at trying to figure out the motion and trying to look at stars. It seemed like some of them wobbled, trying to look at motions of planets and things, trying to look at where things were located in the sky. And he needed to do lots of calculations. So he went through and put every triangle that he was working with inscribed in a circle. And he did this in a way such that the sides became chords. So you describe a triangle in a circle. The sides of the triangle are something called a chord. So the line segment that goes from one part of the circle straight to another part. So these sides here were all chords. And he became interested in what was going on with those chords with respect to central angle, and started looking at measurements with those. Okay, so he started looking at those chords. Like, we take that one chord I drew, and then he'd look at central angle. In other words, angle coming from the center of the circle out to that chord, and he'd look at those triangles there, and triangles that way. And as he was studying these, he needed to know about the different. He had to know quite a few things about not only spherical triangles but also some planar triangles. Because he was looking up in the sky, and really he was dealing with spherical triangles because the sky's nice bowl up there, and then also thinking about like heavenly bodies that are round. But then he had to know something about planar triangles in order to work with them. And as he's looking at these, and looking at that chord in terms of the central angle, he starts looking at trig ratios like sine. And that word sine ends up coming from some of the words for half chord. Like you have a chord there. If you draw that triangle, I'll draw it out here so it's not in the circle anymore. And if you draw this, here's the full chord right here. If you let this be 1 unit and this be 1 unit, if you let the radius of the circle be 1 unit, and you're looking at the angle theta here, half of the chord is actually equal to the sine of theta. Sine of theta equals half of that chord over 1. So that equals half of that chord. So literally looking at half that chord, that ends up being sine of theta. But where did that word come from? Why was it called the sine? Well, it really first started being called sine in an ancient Hindu treatise. Ancient Hindu treatise. There was a gentleman. I'm probably not pronouncing this anywhere correctly, so I apologize, but it looks like it's Aryabhata. If you know how to pronounce these, please don't hesitate to contact me and let me know. I'd love to learn. He lived around 475, 476 or so. So probably 475 to 550. It's about when he lived. But he's used this word. I'm not even going to try to pronounce it because I don't want to butcher it. But he used this word to mean half chord. So in referring to that half chord there that Hipparchus had worked with when working on looking at stars and drawing triangles and trying to look at relationships between stars and planets and such. But it wasn't until this gentleman that we started referring to it as half chord with this word, or you could turn it around. You could reverse and do this. So you could go either direction, chord half, and that can be shortened to this. Okay, so the Arabs came along and they translated this. Arab translation of that nice short word there, I'm going to guess jiva, but the Arab translation of that, they just used this same word, but it started getting, it could get pronounced other ways. So when they pronounced it with one of these variations. And the second one looks the same, so I'm not sure what the difference is. But one of these variations in their pronunciation of that word ends up meaning bosom, fold, or bay. Okay. Latin, another translation. It's like this complicated thing till it got to us. Latin for that is sinus. And then sinus in English is sine. So there's this long complicated history of how we came to call that a sine. But that's what it is. It's that half chord that comes from astronomers using drawing both their planar triangles and any spherical triangles inside circles like that. So they were dealing a lot with spherical geometry, but they ended up using circles to work on it. And I keep marking that. I apologize. But let's go ahead and scroll down. Okay, so, and then as time went on, you ended up with cosine, which basically is the sine of the complementary angle. So co for complement. And then sine, so complementary sine. So you end up with that. And then as you're working in circles, you also you've got tangents too. Like if you're working on your circle again, you've got your central angle here going out. You got your chord. Well, if you draw this tangential line here, you've got two angles, we'll call them alpha. You draw this tangential line here, you've got segment AB, and then let's have segment CD. Well, and then the length of the circle, that segment there is R. Well, the segment AB equals 2R sine of alpha, and then segment CD ends up being 2R tan of alpha. So this tangent line goes along with the tangent of that angle. And then cotangent is the complementary tangent. So tangere means to touch. Tangere in Latin. So a tangent line touches the circle in the one point. So we've got these trig ratios that end up getting derived over time too. So they were way back in ancient times, but then, you know, as time went forward, they were still getting used. Once, you know, past the time of the astronomers using it, people were using the ratios for, especially tangent and cotangent, for shadow reckoning with that gnomon, with that tool for figuring out what time of day it is, basically. And trying to find, when they, trying to find tables of shadows, they're basically finding tables of cotangents. And as time went on too, trying to, on the ground, do measurements, you end up with triangulation, like trying to figure out distances to places on the ground. You use triangulation in these basic trig ratios to help with finding distances from there. So then it ended up being very planar, a lot of planar trigonometry for that kind of work. Because on the ground we can pretend it's a plane even though the Earth is round. Because locally it looks flat. So there's just like a quick, short history of some of these trig ratios. Like, where the heck did this stuff come from, and who was using it? So you see that it's been around for a while. Okay, but what are they essentially? They're ratios. You're to introduce them. I just want to introduce them using a right triangle, because to me that's the easiest way to say what they are, what they come out to. Let's say you have a right triangle. So first of all, let's say, what are they? So you have a right triangle. And forgive my drawing here. I am not that great, and I'm just trying to sketch like I would if I were, standing in front of you at a chalkboard. Let's say you have a right triangle with sides A, B, and C. And let's look at this angle here. Let's call that angle theta. Alright. Looking at angle theta, the sine, abbreviated, sine is S-I-N-E, but you could also say sine, S-I-N, or sine of theta. That's found by taking, it's a ratio, it's found by taking your length of the opposite side from that angle and putting it over the hypotenuse. Remember, with the right triangle, you have the right angle here. The sides attached are your legs, and then the side opposite of the right angle is your hypotenuse. That's the longest side. So using that ratio will help you to find that half chord, like we talked about up here in this circle. So the full chord on the circle is this, but right triangle, opposite over hypotenuse. And the cosine is the complementary sign. You can take the complementary angle and find its sine, or find it, and then you get the cosine. But cosine of theta, if you're just going with this angle, don't worry about its complement. Just go with this angle. It's the adjacent over the hypotenuse. But the complementary angle in a right triangle, your angles add up to 100 degrees, or 180 degrees. This is your right angle, which is already 90 degrees. So the other two angles must add up to 90 as well, so that you can add all three up to 180. So whatever theta is, the other angle, I guess we could call it beta or something, that angle is going to be the complement of it. So the sine of beta is opposite over hypotenuse. So it ends up being this b over c, or the cosine of theta is b over c. That's the adjacent over the hypotenuse. And then our tangent is opposite over adjacent. So tangent, you'd have the A over the B, opposite over adjacent. Now if you want a clever way to remember this, just remember SOHCAHTOA. The SOH, you got the S in sine equals the O in opposite over H in hypotenuse. And then for the CAH, you get the C in cosine equals the A in adjacent over H in hypotenuse. And then for the TOA, you have the T in tangent equals the O in opposite over the A in adjacent. So that's kind of a clever little way to try to remember what goes where. Or way I remember cosine is that when you're doing the cosine of theta, you're doing the adjacent side, you're doing the close side over the hypotenuse. And then sine's the other one, is the further side over the hypotenuse. And then tangent doesn't even use the hypotenuse, it uses opposite over adjacent. So that's those three. Then you still have too your cosecant, secant, and cotangent. Okay, and those are the reciprocals of what you have there. Your sine, if your sine of theta is opposite over hypotenuse, then your cosecant of theta is hypotenuse over opposite, which is basically the same thing as 1 over the sine. If your cosine is adjacent over hypotenuse, then your secant is hypotenuse over adjacent. That's the same thing as saying 1 over cosine of theta. And if your tangent is opposite over adjacent, then your cotangent is adjacent over opposite, or 1 over tangent. And if you look at your tangent and cotangent, okay, you got your tangent is opposite over adjacent, cotangent is the complement of that tangent. So it ends up being the reciprocal. Or if you want to think about it as like complementary angles, your tangent of theta would be A over B. Your tangent of beta would be B over A. So the cotangent of theta, B over A, is the same thing as tangent of beta. So you can take your theta, whatever its cotangent is the same thing as the tangent of if it's complementary angle. Then your secant and cosecant work the same way. Yeah, your secant is your reciprocal of your cosine, and your cosecant is reciprocal of your sine, but those two together are complements of each other. The secant is hypotenuse over adjacent. Secant of theta is hypotenuse over adjacent. The cosecant of theta is hypotenuse over opposite. Well, if you do the secant of beta, that's hypotenuse over adjacent, which ends up being also C over A, which is the same as the cosecant of theta. So the secant of beta and the cosecant of theta and the secant of beta are the same thing. So complement each other. So that's how those are related. Okay, so they were, from the ancient people to today, we're using these trig ratios. Now, in 4.2, we're actually going to talk about these trig ratios in reference to the unit circle. And then when we get to 4.3, we're going to take the trig ratios in reference to right triangles and get really in depth with those. So think about this as like a preliminary history lesson. So next we're going to look at these ratios in terms of a unit circle.